Text-to-image diffusion models have come a long way. From generating high-quality images from simple prompts, they've evolved into tools capable of creating entire worlds. But one persistent challenge remains: subject-driven generation. Imagine you want to create a character, say, a cartoon boy with spiky brown hair, green eyes, and a red hoodie, not just once, but in dozens of different poses, outfits, and settings. The model must preserve his core identity while adapting to new prompts. That's the goal: identity consistency paired with prompt diversity. But here's the catch: these two objectives are fundamentally at odds. Traditional methods either sacrifice one for the other. Fine-tuning approaches like Dream Booth require multiple reference images and hours of training per subject. Encoder-based models work well for faces, but fail on animals, objects, or stylized characters. And newer diffusion transformer, DiT, methods, while promising, often rely on complex architectural changes, careful token positioning, and synthetic data that lacks real-world diversity. We present InstructIdentity, a new framework that breaks this trade-off. It's built on three core innovations: latent concatenation, masked conditional flow matching, and a two-stage distilled data curation pipeline, all without modifying the underlying diffusion model. At the heart of our approach is a simple yet powerful idea. Instead of treating the reference image and target image as separate streams, we concatenate them side by side in the latent space. The noisy target latent gets stacked with a noise-free reference latent along the width dimension. This creates a combined latent grid where the left half is the target, what we want to generate, and the right half is the reference, a fixed anchor for identity. Now here's the key. We apply rotary position embeddings, ρP, directly to both regions. These embeddings encode spatial relationships, so even though the reference is static, the model learns to attend across both regions, using the reference as a visual guide while generating the target. But we don't want the model to reconstruct the reference. We want it to transfer identity. So we introduce a spatial mask, a binary grid that blocks gradient updates in the reference region. During training, the loss is only computed over the target half. This forces the model to learn how to condition on the reference, not copy it. This is where the masked conditional flow matching, CFM, objective comes in. Instead of predicting the full denoising step, the model learns to predict the velocity field, the direction and magnitude of change from noisy to clean. By masking the loss, we ensure that only the target region is updated, preventing identity leakage and overfitting. The result: a model that preserves fine-grained features, facial structure, clothing details, color palettes, even under dramatic pose or viewpoint changes. But training such a model requires high-quality, diverse data. That's where our two-stage distilled data curation framework comes in. Stage 1, seed dataset creation. We start with a massive pool of text-to-image outputs from a base model. But raw outputs are messy, poor layout, identity drift, incomplete compositions. To fix this, we use regional prompting. The canvas is divided into regions, one for the subject, others for background or action. Each region gets a specific prompt and mask. This guides the model to generate consistent character sheets with controlled variation. Then we apply generative outpainting to extend backgrounds and recover truncated limbs. This isn't just post-processing, it's part of the pipeline, ensuring visual coherence. Finally, we filter the candidates using CHARIS, our fine-grained evaluation framework. CHARIS doesn't just give a single score. It breaks down performance across 5 orthogonal axes: identity consistency, prompt adherence, region-wise color fidelity, visual quality, and transformation diversity. It uses segmentation, multicolor space analysis, RGB, HSV lab, and both VLM and non-VLM techniques to detect subtle discrepancies, like a slight shift in jacket color or a mismatched eye shape. Only samples that pass stringent thresholds are kept. The result: a small, high-quality seed dataset, a curated foundation. Stage 2, parameter-efficient fine-tuning. We take this seed dataset and fine-tune the base model using LoRA, low-rank adaptation. We apply LoRA only to a minimal subset of attention layers in the DiT architecture. This keeps the model lightweight, scalable, and fast to train, all while enabling robust identity control. The beauty: no architectural changes, no custom encoders, no complex token routing, just a clean, modular pipeline that works across humans, animals, anthropomorphic characters, and animated objects. Now, how do we know it works? We evaluate it against recent zero-shot baselines, UNO, DSD, and OmniControl, using both conventional metrics and our new CHARIS framework. The results speak for themselves. On identity consistency, our model outperforms all others. Even under Debye settings, where models are penalized for copy-paste behavior, we maintain high scores. That means we're not just memorizing the reference, we're learning to adapt. On prompt adherence, we achieve the highest scores. Our model doesn't just follow the prompt, it interprets it creatively, generating diverse, contextually appropriate variations. And on regional color fidelity, we detect and preserve subtle color shifts that other models miss. That's critical for character fidelity. A red hoodie should stay red, not fade to pink under different lighting. Most strikingly, our CHARIS composite score, which combines all 5 axes, is the highest across the board. It's not just better, it's more aligned with human perception. Qualitative comparisons reveal even more. When generating a character midair doing a skateboard trick, UNO distorts facial features. DSD warps anatomy. OmniControl changes the character's defining traits. But our method, structural integrity, color fidelity, and prompt adherence remain intact, regardless of pose complexity. Ablation studies confirm what we suspected: the mask loss is essential. Without it, the model overfits to the reference, producing copy-paste artifacts and reduced diversity. Full loss may converge faster, but it fails in generalization. Similarly, LoRA configuration matters. Adapting only attention layers works, but adding feed-forward networks improves compositional reasoning. Too many layers, and you risk overfitting. The sweet spot: attention plus FFN. So where does this leave us? InstructIdentity is a scalable, efficient, and highly effective solution for identity-preserving generation. It works without architectural modifications, uses minimal parameters, and leverages a data pipeline that ensures quality and diversity. But this is just the beginning. Future work includes extending the framework to multi-subject conditioning, where multiple characters interact, and handling partial or occluded references. We're also exploring integration with other control modalities: sketches, edge maps, pose keypoints, expanding the toolset for creative and technical applications. In the end, this isn't just about better images. It's about better control. About enabling creators to bring their characters to life across infinite scenarios, not by memorizing, but by understanding. And that's the future of subject-driven generation.